Hello, everyone. Thanks for coming. It's Friday afternoon, and I'm sure that there's a lot of other options between beer and more rides in the Tivoli. So appreciate you showing up. I want to talk about Istio and specifically some problems that we are trying to highlight and actually suggest some solutions for this. My name is Endre Sara. I am the VP of Advanced Engineering at Turbonomic. I've been with Turbonomic since we started the company for about 9 years now, and I'm excited to talk a bit about the company and then jump into Istio. Just a warning that I'm actually want to do a live demo, and apparently you have to sacrifice a goat to have a successful demo. And the problem with Friday is that you have to sacrifice a goat every day of the week. So I'm like up to my 5th goat now. I hope the demo is going to work. We'll see. But anyway, so a bit about who is Turbonomic. So the goal of our software from day one was to assure the performance of the applications, providing workload automation by understanding how to keep the whole stack healthy, how to make sure that we assure the performance of the applications by understanding how does it perform, how it consumes resources, how those resources are available from a multi-cloud infrastructure, and how do we drive orchestration to continuously scale and allocate resources to meet this demand, both in a Kubernetes cluster, but across the full stack, both in terms of virtualization, public cloud, as well as the underlying fabric, wherever it runs. And we've been doing this since 2009, actually launched the product in 2010. Not with Istio at that time, but obviously it's a bunch of things. So talk a bit about Istio. This is probably not new. Just for a show of hand, how many of you have deployed Istio in production? So obviously people have been managing traffic, routing traffic in their environment across various applications for a long time with microservices, with a larger number of components and a more elastic, agile environment. This is becoming increasingly complex. So one of the key benefits is with a service mesh to be able to take control. All of this is to primarily be able to manage policies across multiple proxies, across multiple application components, enforce these policies, and also provide visibility and enhanced resiliency into a complex mesh of services in the way that both users communicate to an ingress as well as application components communicate with each other. Typically, the pattern is that you deploy a smart proxy alongside with your services, and you have a common control plane that is responsible for distributing the configuration as well as collecting instrumentation, also providing security for each of the services. And with this comes fairly broad telemetry as the actual proxies route the traffic. They feed data through the mixer, both as they initiate the call as well as they complete the call. So you got really detailed information about how each transaction has performed, how many transactions you're performing, what is the response time of each of these transactions. Really good visibility, a lot of traceability into it. So at this point, you know everything about all of your application components, how they communicate, how many transactions they perform. You can tell if any one of them is slow, but the question is, what do you do with it now? I've got thousands of nodes, tens of thousands of microservices coming up and down, communicating with each other. What do I do? So this is where we start. There are a number of questions that has to be answered that are not answered by a service mesh. While you've got really good control over how your traffic is being managed, and you've got all this instrumentation, and you've got the ability to change the way the traffic routes, you can scale the applications. What it doesn't solve, it doesn't actually assure the performance of the application. It doesn't answer the question of how many instances do I need to be able to satisfy the application demand not just at 10 o'clock, but actually every minute of the day, every second of the day, if you will. Do I need to scale my application horizontally or vertically? Do I need more nodes in my cluster? Do I need to scale them up or down? How many containers do I place at this particular point in time in a node? And how do I manage the underlying infrastructure? How close these microservices, these pods, should be to each other in the context of their communication, as well as other resources they need to consume. So a number of really exciting challenges and fairly complicated at scale, especially if you want to answer this question continuously and actually do something about it. Especially just to illustrate the scale, some predictions that EastWest Traffic is going to be a significant majority of what runs in your data center over the next couple of years. And of course, this depends on your specific business and your specific application. But in general, with the evolution of microservices, obviously the traffic patterns are significantly changing. And it's important to be able to understand and manage this communication between the components. For example, you can have applications that communicate with each other, but they might be co-located. They might be in different availability zones. They might be in different regions. They could be spread across a on-prem or a public cloud provider. And these traffic patterns can continuously change. So while you could try to address this problem by static rules, labels, forcing these pods to run on the same node in a large dynamic environment, this becomes humanly impossible. So what we are proposing is a need for a dynamic affinity that is driven by software, and it is continuously able to manage application performance in the context of how traffic flows, as well as how applications are performing, and of course how they consume all of the other resources. So it's nice that I can put these pods close to each other, but there are a number of other really important factors that you also have to consider. So what if I have a noisy neighbor and I have, say, two pods on the same node that are impacting each other? Obviously, I want to prevent this problem, but how do I do this in a way that I don't sacrifice my application response time? If this particular microservice is communicating with someone else and I don't get the same performance on a different node? Or similarly, what if a node is overloaded? I don't want to starve my other containers. I can fairly easily move this container to a different node, but how do you find the right trade-offs between the compute, storage, I/O resources that they consume and the way they communicate with each other? And then there's a number of other interesting examples in terms of resource fragmentation, where you can have long waiting pods that cannot get scheduled. You can easily solve this problem by moving existing pods over so that you can place additional pods. I'm just illustrating a couple of examples where you can solve individually each one of these problems. But to really assure the performance of the applications, you need to consider all of these things together at the same time for every single component in your infrastructure to truly be able to make sure that you're providing the level of service that you intended to provide. So what do we have? Kubernetes provides a really cool auto-healing capabilities. I can say that I want X number of instances, replicas of this pod running environment. It will always make sure that I have the number of replicas that I specified, but that in itself is not going to assure the performance of the application. This is actually a screenshot from one of our test applications. We are running a web application, measuring the response time and graphing it in Grafana. And obviously, the fact that I'm auto-healing the environment doesn't assure the performance. This is a over the second response time, which is in this case is not acceptable for a particular web service. You can auto-scale your application. You can make sure that you're running X number of containers, but that in itself, especially if it's based on a single metric like CPU threshold, will also not assure that your performance, your response time is what your SLA requires. And it is also reactive. There are a number of things that you have to consider to solve this problem. And in general, how do I continuously scale the environment? How do I manage how these things coexist, especially in a shared environment? We've got a number of large enterprise customers who are providing a shared multi-cloud infrastructure, and there are many application developer teams that are deploying into the same set of clusters. The question often comes up of, do I provision for the worst case? I reserve everybody, in which case it's very expensive. Do I provision for the average, as in offer a best effort service? Typically, they end up with a high failure rate, out of error messages. And in general, how do they scale the underlying infrastructure? And trying to manage this manually, application by application developer by application developer, is really painful. It's almost impossible to guess what is the appropriate memory request or limit that you need to specify without knowing what the actual incoming transaction rate is going to be at any point in time, and especially if the application scales horizontally at the same time. So really, our point is that you have to continuously resolve this trade-off, make decisions on where to place application, where applications can truly run anywhere on any cloud, how to scale these applications with the understanding of the complete stack. And what I mean by full stack is that it's really exciting to be able to easily deploy applications into a Kubernetes cluster, to be able to route traffic through a service mesh. But at the end of the day, this runs on some infrastructure, be that public or private cloud. And you cannot manage that independently without the understanding of the underlying infrastructure. But there's no single human who can look at both the underlying storage fabric or the choice of the storage tiers in a public cloud, the network fabric, faulty NIC cards, while you're also trying to enforce policies at the service mesh layer. So really, our proposition is that you need software to be able to solve this problem. You need to be able to understand the complete stack, make decisions to solve all the previous trade-offs that I mentioned continuously in real time at scale without relying on humans to operate the environment at the second by second or minute by minute level. So I want to illustrate this with a couple of demos. And hopefully we'll have some time for questions as well. So we are running actually several Kubernetes clusters, mostly 1.9, 1.927, Istio 0.7.1 with some Prometheus and Grafana, and we are actually leveraging Turbonomic to manage this complete stack of applications and infrastructure, and effectively preventing application performance degradations. So if I switch over to this, okay. So this is actually the user interface of Turbonomic. Just to illustrate a possible way of solving this problem, Turbo is actually able to tap into several public API instrumentation points. We are leveraging the instrumentation exposed by Istio. We're actually currently getting that through Prometheus. We're managing Kubernetes through the Kubernetes APIs, either running on Azure or running on a on-prem VMware environment. But we've got a fairly large selection of combination of layers of stack, types of applications and infrastructure that you could run on, be that Istio or Cisco Tetration, be that any hypervisor as well as any cloud between. Typically, most of our customers are running on either AWS, on Azure, or some on-prem cloud. And by simply interacting with the public APIs of these different components, we are building a single common abstraction, a single common representation of the complete stack, stitching it together continuously in real time, understanding what are the applications that are running in the environment, what services they expose to end users or to each other, what containers they're running on, in what pods they are being deployed, all the way down to which, in this case, they're running on an on-prem virtual environment, what virtual machine they're running on, what hosts, what data stores they are leveraging. And really, the goal of our software is to resolve these trade-offs continuously by driving a set of actions that are both deciding on how to scale horizontally, vertically applications, how to reallocate resources, such as reschedule a pod from one node to another, and of course, how to scale the underlying node itself. To drill into one of these examples and kind of nailing it down to Istio, so this is actually a fairly simple application that we deployed. A client and a server application. This happens to be the client part. It's actually running in a pod with an Istio proxy, so that we have the ability to both instrument and to control the traffic. This particular pod is running on a Kubernetes node, which happens to be hosted on one of our HP servers. And really, what the instrumentation allows us to do is to look at how much network traffic is generated by this application. And it died. Okay, I guess it wasn't enough goats. So anyway, so the point is to be able to decide where these pods should be running, and if I go back here, is to be able to take any one of these pods and place them closer to their bodies. Now I am demonstrating the actual ability to control this in manually, but really our system is designed to automate these actions and continuously control the environment. What most of our customers are doing is they are basically letting our software to automatically control the environment. So all these decisions that our software is making based on the real-time changing demand are actually executed by our software, closing the loop in a Kubernetes cluster, on a public cloud, or an on-prem environment, by actually taking these actions and, of course, maybe changing them as the workload demand changes. And to illustrate a couple of other use cases, it's of course not enough just to manage the applications in terms of their placement, but also in terms of their scaling. So what we have here is another application that we are generating a relatively high amount of traffic, and both through our user interface, we can see the transaction rate and the response time of the application. This is also actually coming through Istio and Prometheus, which we can also see through Grafana. And what our software is identifying as an action is to basically provision an additional instance of this container, which then in turn will scale the container out. And what's really important is that while I was showing how bad the current response time is, that is not the only factor in deciding how to scale the applications. We are looking at the combination of the available resources within the cluster, how far can I scale this application, and in general, how many instances do I need to be able to assure the performance. So understanding the complete stack informs the decisions that our software makes and closes the loop much more comprehensively than if you simply took a single metric or some calculations on a combination of metrics and scale the pod either manually or through some methods. So that's most of the demo, actually. So I don't know if there's any questions or comments anybody might have, and I think there should be a microphone somewhere in the middle. Okay, in that case, I'll hang around for a bit longer, and thank you for coming.